All right, everybody. So here's the thing. I want to just kind of explain what this problem is about. So you're looking at this from above. This little mass goes down this ramp, and then it kind of goes in a circle around this wall here. And basically what they're doing is it's kind of like you're flipping this cardboard like up, like this, so that you're kind of looking at it from above and seeing what's going on here. Oh my gosh, come on. You're kind of, it's like you're looking at it from above here. And I know this is some obvious stuff, but I just want to be clear. This is the side view. This is the top view. This thing here is the rough wall. Like that's the rough wall right there. It's there and there. And the smooth ramp is this thing right here looked at from above. So we're going to go down this ramp, and then we're going to actually go around the circle and kind of stop. So let's just look at a couple things. First, it says derive an expression for the height of the ramp. Look, I've got a height, I got a mass. There's just not a lot I can do here. I'm really thinking conservation of energy. Except they're calling the speed at the bottom V naught. I mean, fine, they can call it that. So H is going to be V naught squared all over 2G. Now, after a short time after passing a point P, so a short time, this is a short time, let's just say, the block is in contact with the wall and moves at the speed V. Okay, so the vertical component of the force. I'm going to actually look at this from like the top view. So it's like we've got the block right here against the wall. And what we're saying is there's the normal force from the ground and like the downward force of gravity. And basically the net force, the net vertical force on the block is 0 because it doesn't move up or down. I'm sorry that was such a disappointing answer. In fact, I don't know, I put a 0 there. Okay, fine. That wasn't supposed to be a 0. It's supposed to be a mark there. Sorry, I cleared my throat. I hope that wasn't too loud. All right, on the figure below, we're going to draw an arrow on the block to indicate the direction of the horizontal component of the net force. Okay, let's be clear. It's moving in a circle, so the net force is moving it in a circle like this. And to be clear, the only force that's actually on it horizontally here is the normal force from the wall. What we're also told is that this is a rough wall right here. So that tells me if it's moving this way along the wall, the friction force is going that way. I'm going to label that as well to let you know the friction slowing it down. Oh, there's a direction to this friction force. If you notice, if this is a circle, then this line is tangential to the circle. Just like in calculus, a tangent. This will be important later. So what does the normal force do? It makes it move in a circle. So this is the best we can do. We can say that the normal force makes it accelerate in a circle. So the best we can do to solve the normal force is it equals mv squared divided by the radius. And then here's another sad part. We're going to derive the expression for the tangential acceleration of the block. Check this out. The tangential force gives me the tangential acceleration. So it's the friction that makes the mass accelerate tangentially. So that's going to be ma tangential equals mu times the normal force. So we isolate, and we're getting the tangential acceleration is mu times v squared over r. What a great problem. I can hardly wait to publish this to video and take a look at the last problem on the practice test.